Can you see my video?
Yeah.
Okay, okay, I can't even see. Okay, that's
We'll give it like 2 minutes for people to join and
okay.
start with the intro. All right, let me make it start. Hello and good evening, everybody, to our ICorr Aberdeen March 2024 webinar. The topic of presentation today is advances in comprehensive integrity assessment of buried pipelines with non-contact magnetic gradient tomography method, MTMG. Presented by Dr. Candidace Chukwuma, who is now currently residing in Canada. So a few points to make before we make a start. If you require CPD, please fill up the survey at the end of the session with your full name and your email address. And also, if you've got any questions for this presentation, please put them into the Q&A chat box and we'll address it at the end of the presentation. First and foremost, I'd like to thank the 2023-2024 Aberdeen Branch Committee and also our sponsors. And the next branch program will be an industrial visit to NCIMB. It's gonna take place on the 23rd of April at 6 p.m. So please be on the lookout for the next announcement and to find out how to register for the event. And for our speaker for today is Dr. Chukwuma. He's a president and principal corrosion consultant of Ken Sharks Corrosion Incorporated Canada. Prior to this role, he was the global product manager at Xylem for corrosion, covering cathodic protection and overlying survey technologies. Chukwuma holds a Master's of Science in Corrosion Control Engineering from the University of Manchester in the United Kingdom. He also has a doctorate in materials engineering from Dalhousie, sorry if I'm not saying it right, University, Halifax, Nova Scotia, Canada. He has managed several corrosion materials, pipeline integrity, and direct assessment projects, including ECDA, SCCDA, and ICDA, and also has authored more than 40 corrosion technical papers and has conducted research for the Pipeline Research Council International, PRCI, and is a fellow of the Institute of Corrosion, ICorr, and an AMPP certified corrosion specialist. So please put your virtual hands together for Dr. Chucks, and I'll hand that over to you.
Okay, thank you. Thank you for the introduction, May. Just confirm, can you see my screen?
Yes.
Okay, hello everyone. As main
sorry, I don't think you're sharing your screen yet. Right, okay.
Can you see my screen now?
Yes.
Okay, hello everyone. As main introduced, I'm going to be covering the advances in comprehensive integrity assessment of buried pipelines with non-contact magnetic gradient tomography method, MTNG. In the outline, I'll start with the introduction. I have some slides on the introductory topics. Then I'll cover MTNG and pipeline integrity improvements. I'll be focusing on the unique benefits of this technology, and then real-life case studies and conclusions. At the end of the slide deck, there are some reference information, and also there's a contact details, maybe because of time, or if somebody has, or if there's a lot of questions in the Q&A, my contact email is there for follow-up. So there are 3 approved pipeline integrity assessment techniques. So the first one is hydrostatic pressure testing. inline inspection, and direct assessment. So generally speaking, for hydrostatic pressure testing, this involves pressurizing a specific pipeline segment in the presence of water or another fluid to a specific pressure, and then monitoring the pressure drop, which can indicate the presence of leak or weakness of that specific pipeline. It is intrusive, it is a destructive test, and it's also non-predictive. You can't really use it to predict, in a future corrosion growth analysis. The second one is inline inspection. It is intrusive, that you deploy your inline inspection peaks. It's non-destructive in the sense that you're not going to have any impact during the inspection. It is reactive in the sense that the defect has to exceed the detection threshold before it can be used. The last one, which is the focus, most focus on my presentation today, is going to be on direct assessment. It's non-intrusive. You can have your above ground inspection tools like evaluating the effectiveness of cathodic protection, coating conditions. Like there are several tools for coating assessment, like direct current voltage gradient, DCVG, alternating current voltage gradient, ACVG, alternating current attenuation, ACCA, and also looking at the soil conductivity. All those information are used to be able to evaluate and predict the likelihood of external corrosion. So it can be conducted while the pipeline is in service, it is non-destructive, and it is predictive. And also for the internal corrosion assessment on non-piggable lines, we can use the pipe elevation profiles and robust and proven flow modeling to be able to predict water and solid accumulations. And from there, we can make an inference about the condition of that line. So every technique has pros and cons, but when it is practically possible, combining two different tools, ensure holistic assessment of pipeline. So this slide deck is just giving a summary of different assessment techniques. So for the first one is inline inspection. It is reactive, intrusive, and non-destructive. So we use one of the most effective ways of assessing pipeline integrity, determine the pipe loss or metal loss on a specific line. For the direct assessment is proactive in the sense that we are able to capture the effectiveness of cathodic protection, coating conditions, soil, and there are 4 different processes from the pre-assessment, which is the desktop assessment, where we gather information about the specific line. And then the step 2 is the indirect inspection, where we work and evaluate, collect information that we use to predict the likelihood. And step 3 is when we expose the line. And the final stage is the post-assessment. I'm going to cover details in the next slides. Hydrostatic pressure testing is intrusive, destructive, involve filling the pipe with water and raising the pressure to a above normal operating range to check for leaks or ruptures. Second one is assessment of output. For the inline inspection, it provides full coverage of the pipe wall, reports defect size above the 2 detection threshold. For the direct assessment, it's proactive and it predicts the susceptible location for external corrosion, or for stress corrosion cracking, or for internal corrosion for ICTA. For the hydrostatic pressure testing, it provides full coverage with no quantitative defect data. Only defects that fail during the test can be seen. So it doesn't provide information about the subcritical defect. In terms of deliverables, inline inspection is one of the most pipeline assessment technique. It provides clear indication of the defects on the pipe wall and the location of the sizing at the time of the inspection. For the DA, since the pipe is exposed, after the indirect inspection, the pipe is exposed and the NDE can be conducted to actually confirm the condition of that specific segment. For the hydrostatic testing, is a pass and fail indication that captured at the time of the inspection. So for limitations, inline inspection is reactive, so defect has to exceed the detection threshold before it can be used, and it's also intrusive. And in most cases, before the inspection is conducted, there may be some modifications that may be required to be able to complete the assessment. For the DA, the right-of-way condition, the coating type, the depth of cover, there are other factors that can impact the success of that assessment. So for instance, if there are some interference issues that have not been resolved, or depth of cover exceeds the threshold for above ground technique, or maybe the coating type is a shielding, high dielectric shielding dielectric coating, it may impact the accuracy of direct assessment. For hydrostatic pressure testing, in some cases, disposing the water can be an environmental concern. And also, if the water is not properly treated, it may pose some issues from the internal corrosion standpoint. So each technique has strengths and weaknesses, but as diligent practitioners, it's our role to be able to understand the limitations so we'll be able to use it appropriately. So this is a research, it's FYI, this is an old research done by Dr. Neil Thompson. He just gives a high-level overview of different assessment techniques in terms of the cost, in terms of the challenges that can be encountered prior to inspection. In the hydrostatic, in the inline inspection, there may be, the pipe has to be prepared, and also there has to be an inspection. So this study covered the cost of preparing the line and the cost of the actual inspection. In the hydrostatic pressure testing, the pipeline has to be prepared, and there may also be an impact on the operations. Then in overall, if you look at the three pipeline assessment techniques, from cost, inline inspection based on this research is number one, followed by hydrostatic pressure testing, and then direct assessment. So, but the key information here is, if you're looking at the DA, which is a direct assessment, it is actually very good in terms of avoiding interruptions, and there's no preparatory requirement for the pipeline before the inspection is conducted. If you are trying to evaluate the cathodic protection effectiveness, you can work on buried pipeline and you conduct your inspections without having any impact on the operations. So DA can be applied. There are three ways, types of direct assessment. The first one is external corrosion direct assessment, which is the ECDA. This one focuses on looking at the effectiveness of cathodic protection, looking at the coating conditions, like predicting the coating condition from above ground, and then using the soil conductivity to be able to predict the likelihood of external corrosion. In step 3, which is a direct assessment, the pipe is exposed and NDE are used to be able to evaluate the actual condition. In step 4, which is the last stage, which is the post-assessment, the effectiveness of the entire program is evaluated and the reassessment interval is established. For instance, in the US, if it is a liquid line, CFR Part 195, if there's no internal corrosion found, or if there's no corrosion found for liquid line, the next reassessment interval is 5 years. But if it's for gas line, CFR Part 192, if there's no corrosion found, the assessment interval is 7 years. So the next one is stress corrosion cracking direct assessment. We're looking at the previous history, the type of coating, the age of the line, the stress level, temperature, stress level. All those information are evaluated to be able to predict the likelihood. Internal corrosion direct assessment, proprietary and proven internal corrosion software are being used, plus pipe elevation profile, plus the operating parameter of the line, plus historical information to be able to predict water and solid accumulation and concurrent internal corrosion rates. So these techniques can be applied to both piggable and non-piggable lines. It's a systematic and thorough 4-stage processes. The step 1, you gather all the information, you confirm that you can actually conduct the inspection, be it internal corrosion, be it external, be it stress corrosion cracking. In step 2, you predict the suspected corrosion locations. In external corrosion direct assessment, that is when we actually walk. So in step 1 is a desktop study. Step 2 is walking. So we're actually walking on buried line using the above ground tools like CP tools, coating inspection tool like DCVG, ACVG, ACCA, and then using 4-winner pane or Geonics, which is using the electromagnetic technique to be able to evaluate the soil conditions. So once we complete that inspection, then we gather all the information, then we classify and prioritize and look at the areas that have been suspected for external corrosion. And then in In step 3, this is when we are actually exposing the line to confirm the actual condition of that specific line. So that is when we use our NDE techniques to evaluate the actual condition. And the step 4 is a post-assessment. So in all the techniques for the ICDA, ECDA, and XCDA, these 4 steps are followed. So step 4 is when we actually evaluate the effectiveness of the entire program and confirm that the process is actually effective. So this just shows specific locations, just giving a broader picture showing where those types, DA types are shown. For the external corrosion is external, outside of the wall. So the focus on the cathodic protection effectiveness, coating conditions that is being predicted from above ground using direct current voltage gradient DCVG, alternating current voltage gradient ACVG, alternating current attenuation ACCA. From the stress corrosion cracking on buried onshore lines, it is covered in AMP SP0204 2015 standard. You're looking at the previous history, you're looking at the age of the pipeline, the coating type, the stress temperature, distance from compressor or pump station, depending on whether it's a dry or liquid line. And that information is integrated with other information to be able to predict the likelihood of external stress corrosion cracking. The ICDs, there are different types, which is dependent on the product, wet gas, liquid, dry gas, and multi-phase. AMP has very good standards that shows how they are addressed. So in real life, we actually collect the pipe elevation profile, and then we use the operating parameters and previous history to be able to predict water solid accumulation, and there are proven robust internal corrosion flow models that are very accurate, that can give you the concurrent internal corrosion rates. When that information is gathered, it can now be used to make an informed decision on the specific condition of that line. And then the pipe can also be exposed during step 3 to confirm the condition. So for external corrosion direct assessment, it's covered in NACE. You can see some NACE on my slide deck, but it's changed to AMPP. SP0502. So the key is that the likelihood is dependent on confirming the levels of cathodic protection, coating condition, and soil resistivity. So in ID condition, locations that have improved or effective cathodic protection by AMP SP0169 standard has very good coating conditions, should not have external corrosion. So if the CP is inadequate and there's extensive coating anomalies, maybe the steel is not exposed to the conductive environment in a conductive soil. So with those 3 conditions, external corrosion can be predicted. So, so looking at the condition of the coating, the effectiveness, and the soil, the likelihood of external corrosion can be predicted. So before we conduct the assessment, we first of all do a pre-assessment. So we're trying to evaluate in step 1. We are evaluating conditions that can impact or preclude the success of this program. We're looking at, can indirect inspection be completed on the right of way? Are there conditions that can impact the success of the program? For instance, if the pipeline right of way is in a very deep creek or river crossing that cannot be assessed, can we successfully conduct the indirect inspection? Can we successfully conduct the direct examination? If it is for ICDA, can we able to capture the pipe elevation profile? Can we be able to model and complete our direct examination or detailed examination? So how deep is the pipeline is buried? Do we have a high shielding dielectric coatings that can impact the accuracy of the data? So these are the questions we ask during the pre-assessment. In step 2, that is when we actually walk on the buried line. So there are different techniques. The CP6 means cathodic protection closed interval potential survey. This is used to evaluate the effectiveness of the entire cathodic protection for the entire buried lines. ACVG, I've said it several times, alternating current voltage gradient. DCVG, direct current voltage gradient. ACCA, alternating current attenuation. These techniques are used to be able to evaluate the condition of coating. So we are actually predicting from above ground. The actual validation is when the pipe is exposed to this step 3, and NDs are used, visual inspection techniques, to be able to validate the condition of the coating. In addition, we also collect soil to be able to evaluate the conductivity of soil in that specific area. This slide deck shows an above ground technique. It mimics the way the inspection is done. So you see the technician with 2 probes conducting the coating voltage gradient survey, and you have seen your copper wire connected to the test post for your cathodic protection survey. And there are some robust tools that can be used to be able to collect all this information in one pass to enhance data collection, efficiency data protection, efficiency data evaluation, and the accurate prediction in the condition of buried line. In step 3, that is when we actually identify and align those indications. So where we have coating anomalies, locations with inadequate cathodic protection, highly corrosive soil, that is when we integrate those information, then we classify and prioritize. If we have additional information from inline inspection, we can actually integrate everything together to accurately pinpoint the location that has high propensity for external corrosion. If you can see from here, this red line shows the anomaly zone. The CPC shows that this pipeline has adequate protection. You can see the blue line, the drop in current level suggests that there's a loss in current leaving the pipe at that specific area the coating fault is. There's increase in the voltage gradients that suggests that the current, that coating exposed line is, the current is flowing in that area, and it generated a voltage gradient that can be captured from above ground. So from here, it can easily be seen that there's something going on here. So that location was actually exposed during the direct examination, and as predicted on the left-hand side, the actual condition of coating was validated during the direct examination. So the direct assessment tools, they have grown so strong that you can actually use it to be able to predict the actual condition of pipe before the pipe is exposed. Then during the post-assessment, we evaluate the effectiveness and then determine the reassessment interval based on whether the corrosion is found or whether there's no corrosion found. So for the stress corrosion cracking direct assessment, so the evaluation is based on, looking at the levels of cathodic protection, looking at the history, operating stress level, distance from compressor or pump station for if it is for liquid, operating temperature if for high pH XCC, age of the line and coating type. So all this information, they are gathered to be able to predict the location that may be prone to XCC. So looking at the environmental, the metallurgy, and the stress. So for the specific buried line to be susceptible, the environment, the pipeline must be exposed to the environment conducive to XCC. Say for instance, if the pipeline is stressed and there's a coating fault and that environment is susceptible, so that bare metal is exposed to conducive environment through that coating fault. And that is why having indication about the condition of the coating is critical both for ECD and XCCDA. Similar to ECDA, we do the pre-assessment, which is more of the desktop study to be able to understand the likelihood. We're saying in the office, we're not going to the field, we're looking at the previous history, looking at the stress level, the age of the line, we're looking at the kind of coating, we're looking at the temperature, we're looking at the distance from the compressor station. So we're gathering all this information to be able to predict the likelihood. These details are covered in AMP SP0204 2015 standard. I believe that's the latest standard. And once the pre-assessment is done, in order to go to the next step, we also have to go to the field, go to the buried pipeline, to be able to gather additional information from the cathodic protection effectiveness, the coating conditions from above ground. And this LSM is what I'm going to be covering today. There's a lot of trade names like LSM, stress concentration tomography, pipe wall assessment, MTNG. So this is also helpful in the evaluation of external stress corrosion cracking. Getting information about the stress concentrations can be used, integrated with all the information to be able to help align and predict susceptible locations. After that, then we align all the indications, know where the coating anomalies are, locations of insufficient PP, stress concentrations, and if the pipeline is piggable, we can take information about where the external metal off is cut out, dents, areas of coating disbondment, on a high shading the electric coatings. All this information are integrated to be able to classify and predict and refine specific location that may be put into XCC. After that, the final stage is not the post-assessment. So depending on the outcome of the direct examination stage, the exposed line is evaluated, and from there, the presence of crack is validated, and that can help to establish a reassessment interval. So let me take a break, take a sip of water. And then I'm going to the main topic for this discussion. I'm going to go into non-contact magnetic gradient tomography method, MTNG. So this is a new technology that can be used from above ground in addition to the CP, CIPS, DCVG, ACVG, ACCA, and with the soil information to be able to help operators, especially on non-piggable lines, to be able to evaluate external metal loss, cracks, dents, and all sorts of issues on the line. And this slide just shows some. These are not all. These are just some pipeline reasons that can come pipeline failure from corrosion, cracking, weld failure, and external forces, third-party damage. So these are just some of them. In terms of pipe inspection methods, to conduct peaks, it is internal. The tool has to be deployed inside of the line. There are some smart peaks, robotic tools. Externally, that is a contact base. There are tools like UT, they can be used outside of the pipe. Some of these ND techniques I mentioned on the slide deck, they're used outside, and they have to have a specific contact on that pipeline to be able to evaluate the condition. So this is just introductory leading to the MTNG and how it works. So every technology, every tool has strengths and weaknesses, and there is no solution that is 100%. If you want to conduct your inline inspection, there has to be some pipeline preparation required. In some cases, the operators may have to install some launchers and receivers for the peaks. In some cases, the pipeline can be non-piggable entirely, and it is isolated. And in some cases, the anomalies may not be in the range, or maybe in the critical range that may require a specific tool to be able to evaluate that. So every inspection technique has strengths and weaknesses. The bottom line is the best way is trying to understand the strength and use it at this specific instance. So overall, no specific integrity solution is 100%. There's strength and weaknesses with any technique. So according to ASME, or according to industry best practices, the focus more is on the defect size and the flow stress of the material. But if we can include information about the mechanical stress, that will be able to help to evaluate the condition of that specific line. And that is the background of this MTNG that I'm going to be I'm going to be covering the next slides. So if we look at this slide deck, look at two defects. The second one is at the bend. They have the same defect size. So the one at the bend, if we can gather information about the stress combined with the defect size, that will help ensure a holistic evaluation of that condition of that line. So having information about the stress in addition, and just FYI, this technology is best used in addition to ensure a comprehensive assessment of that specific line. So this cartoon, I give credit to Seamus McDonald. He was a person that was demonstrating the IPC 2018. It shows a way that this non-contact magnetometry works. So you have a magnetic moments that are neutral. When the stress is applied, it's going to affect their orientation that will generate a magnetic dipole, and that dipole is a result of stress concentration And that is what we're measuring. So for instance, if I'm doing a coating survey, I'm looking for where there's increase in voltage gradient. That infer that there's an exposed line on that specific area. Or if I'm doing a coating attenuation technique, I'm looking for where there's a significant current loss. That suggests that there's an exposed pipe where the current that is being applied is being leaking off. If I'm doing a magnetometry technique, I'm looking for where there's elevated stress concentrations. And we're using our magnetic sensor from above ground, walking above on buried pipeline, and be able to capture where stress concentrations are. And that can be indicative of the specific defect. It can be metal loss, it can be crack, and it can be strain, it can be soil movement. So the way it works is that you see the steel pipe with a neutral set of magnetic moments. And this cartoon is going to do a good job explaining how it works. So apply, stress is applied. Oh, sorry. Let me go back. Next slide. I don't know why the cartoon is not showing. Okay. Stress is applied. The magnetic moments are aligned. So you see the magnetic dipole. Oh, so I don't know why the cartoon did not show. But anyway, so that's basically how it works. I will check. I don't know why the cartoon did not show. So the technicians are working, and what we're capturing is where these stress concentrations are. You can see from here, this is the area of the stress concentration, and that is where the defect is. And then the next step is it has to be characterized and prioritized. So even before these presentations, I got a lot of feedbacks and questions on LinkedIn, and I just wanted to make sure I addressed them here. So this technology has other trade names. The magnetic tomography, gradient tomography method, MTG, is the technology now that has been extensive R&D has been done to be able to improve it to the level that it becomes a very reliable tool to help operators evaluate the condition of their line. There are other trade names, stress concentration tomography, pipe wall assessment, and large standoff magnetometry. All of them are the same methodology, share the same methodology. During the inspection, the electromagnetic pipe locating, the GPS mapping, and all the inspection are integrated in the same survey. They are, depending on the right-of-way condition, it can also be done where the pipeline is located and the technician can walk behind to be able to capture stress concentration areas. This technology can be applied on both onshore and offshore lines. In terms of the limitations, this technology can only use if the depth of cover is within 7 meters. Anything above 7 meters, the probability of detection may be questionable. So provided the depth of cover is within 7 meters, you can use this technology. So it has a limitation. It's not a perfect tool. It has limitations as well. So how it works is the technicians walk. They have the magnetic sensor. They're working on buried line right of way of the pipeline. And if there's areas of stress concentration is being captured, and that can be indicative of the defect on that line. After the inspection, the data is being processed and analyzed in the proprietary software where all anomalies are classified and prioritized. In terms of the deliverable, so the anomaly in locations are going to have the GPS locations and above ground markers. So if the technician is walking, there's a test post or there's a valve or there's something that can be tied to inline inspection or tied when comparative correlations are being done, that will help an operator pinpoint the specific area of interest. It's not just the GPS. The AGMs also help to know, for instance, if there's a valve station, so the technician is going to mark that and it's going to appear on the report or the deliverable. So the GPS plus above ground markers also help operator to be able to align to where those indications are. I'm looking at my time here. So pipeline defects, according to fabrication, are usually identified before the pipeline is buried against industry best practices. But however, we know from operation, as a pipeline is there, it begin to develop some stress concentration, which can affect, it can impact the failure, stress failure, It could be cracks, it could be dents, it could be buckles. So generally speaking, if these indications are proactively managed or proactively identified, it can help to improve safety, and it can help to save costs in downtime. So having a tool or implementing a proactive integrity management where these defects are proactively identified will help a long run ensuring safety and minimizing risk. So this MTNG is non-destructive. The technicians work from above ground. As I said earlier, the key limitation is the depth of cover. It has to be within 7 meters. And also the length of the line has to be above 100 meters. And then they are working from above ground with a magnetic sensor, and they are able to work from above ground, even from buried, above grade offshore pipelines, to be able to determine areas of stress concentrations. So through capturing those change, and I wanted to add a new point as well. So this technology is heavily useful for the non-piggable lines where deploying inline inspection may not be practically possible. It can also be used on piggable lines. Say, for instance, is a critical line where the operator, it has a high consequence of failure, and there's a criticality in that defect. Operator can supplement this in addition to the inline inspection to ensure a holistic evaluation of that line. The change in the magnetic field, which is as a result of stress in that specific line, so that change is what this MTNG is measuring. So the change in the magnetization due to the mechanical stress, like in my cartoon, once the stress is applied, it changes the magnetic moments, it creates a dipole, and that dipole is as a result of stress concentrations, and that is what the MTNG detects. As I said earlier, every technique has a methodology, but this one is focusing on measuring the stress level. On the right-hand side, this technician is working with a magnetic sensor, working on a buried line. This inspection in real life is integrated with the pipeline locator with the GPS. So as he's working on the right of way, he's capturing areas of stress concentrations. You can see from on the left-hand side, this is where there's increase in stress level, which is a result of stress concentration. So this is the area of concern. Once all these areas are being captured, the technician goes to office, and then the proprietary software is being used to be able to characterize those defects in terms of what is actually going on. What defect am I capturing? Is it metal loss? Is it crack? Or what is it? Looking at my time, so this technology can be used to detect cracks, metal loss, weather anomaly, geometrical changes like dents, metal loss localized, stress-deformed conditions like soil movement, soil erosion, landslides, and areas of discontinuity. So this slide deck is going to be shared. So if any person has specific question, you can contact me. So this slide deck is showing the key improvements like identification of pipeline anomalies, before the inspection is deployed, before the tool is deployed, the POD, which is the probability of detection, is confirmed to ensure the confidence in data collection. And then after that, the fieldwork is done, and the characterization is now, what is the actual defect did I capture? So if you see an increase in elevated stress level, what is actually causing that? Is it a dent? Is it a metal loss? Is it a crack? What is it? So this tool is able to characterize based on the robust and appropriate software to be able to tell you exactly, you be using the signature of that dipole to be able to pinpoint exactly what the defect type is. Then after that is a prioritization. What is the criticality of that defect? How can an operator use that to be able to evaluate and prioritize areas of concern? And so this DA can be combined with already industry available tools like the CP tools, the coating tools like DCVG, ACVG, ACCA, plus soil information to be able to enhance the confidence in the evaluation of non-piggable lines. So like the DA practitioner, they have seen this is a new tool that can be supplemented to ensure a holistic approach of the evaluation. And then on the right-hand side, you can see from here, on the right-hand side, you can see from here, it shows the priority. You can see the green, red, and yellow. This red means severe, moderate, and minor. So the operator is able to see from spatially the condition of that specific line. Okay, have less than 10 minutes to go. So, so in terms of the POD, looking at, oh my goodness, look at in terms of the POD. Before we start the field work, we confirm what the POD is. If it's for mental loss, over 80%, for longitudinal stress, 85%, and for complex SDS, 95%. Once that is confirmed, we'll be able to start the inspection. So the key is before the inspection is done, we need to confirm that we can actually characterize and prioritize. On the right-hand side, this is a defect that was being predicted with this tool, and the pipe was exposed and it was confirmed. This shows how the data is being presented. So different defect types are characterized, and the GPS of start and end and the specific area is being shown. Is it a crack-like, metal loss, weld, geometrical change, SDS, metal loss? All those information are being characterized to let the operator know exactly what is going on. In terms of the prioritization, there are some specific proprietary ways and also other ones based on best practice, like the beta state. That tells you 3 is minor, 2 is moderate, and 1, there's no 1 here, is severe. So based on the stress concentration and other factors, we'll be able to prioritize. Like this one now, anomaly 1 has weird anomaly, and there's a stress anomaly in that, stress deform anomaly in that area as well. So this technology is able to uniquely identify area where there's complex or multiple anomalies acting on that specific area. And then the risk factor is also used to be able to evaluate the risk level. And then these are just general best practices like the ERF, which is the MOP over the safe operating pressure of the line. And then this has a nominal wall thickness, and this is the predicted metal loss. I'm going to talk about the estimated metal loss in the few slides, while I'm also looking at my time. I have less than 5 minutes to stop. So this shows how the technology can be able to classify and prioritize. So the client is able to know exactly the priority. What am I dealing with? Is here a weird anomaly, which is what this one is, and what is the priority level? So this one requires urgent attention. So the operator is able to know that right away from the data. It's also able to capture the strain. This specific, the meta state, look at the 1. So 1 means, let's say severe from here. So that is the way it's classified. And then from the metal loss, we are able to give the specific metal loss on that specific anomaly and also calculate the remaining life. So this, once the magnetic stress is measured, the metal loss can be estimated using the ASME B31G and other proprietary algorithms. So this is a real-life case study where the client was interested in using this technology to be able to identify areas of concern. So the metal state here is 2, which is moderate, where the anomaly was detected, and then plus hoop stress, external metal loss, and the pipe was exposed, and it was validated. So MTAG was used first, preliminary, to be able to predict areas of concern, and NDE vendors were employed to be able to validate that. So the last one, as I'm running out of time, is on a scenario where inline inspection and MTAG can be employed. 1, MTAG measures the magnetic field gradient and provide detailed insight into mechanical stress present in a pipeline, including hoop, longitudinal, and complex combination like bending and shear stresses. Inline inspection is the best tool for detecting physical and geometrical anomalies within a pipeline, such as corrosion, metal loss, and crack. So when these tools provide detailed information about the geometry and orientation. In the integrated scenario, when 2 of them are combined, they can offer a comprehensive view of the pipeline condition. For instance, MTAG can measure metal loss through magnetic field gradient. IRI can provide information about the geometry and location of defects. So this complementary integrated methodology allows a thorough and a comprehensive assessment of that line. So if they are combined, taking advantage of each specific strength, this synergetic relationship can improve the identification of potential risks and help operators address areas of concern. So when the defects are, this industry best practice are being used to be able to assess the specific defect. So MTNG is also very good. Once the stress is measured, industry best practice are being employed to be able to get you the safe operating pressure, stress concentration factor, the ERF. All those information are being used to evaluate the condition. So the last case study I'm showing here is a 26-inch gas line in service in 1980. Inline inspection MFL was used to be able to evaluate the condition. And in addition, the operator wanted to validate this technology. So what did they do? They deploy MTNG in that specific line to be able to identify areas of issues. So MTNG was employed, and the keynote I wanted to share is this technology is designed to measure the magnetic stress that is being used to back calculate and estimate the geometrical wall loss. So it's not designed to measure metal loss or geometrical metal loss, but it's designed to measure the magnetic that is back calculated to estimate the geometrical metal loss. And the intent of this was to confirm the accuracy and the detection, the probability of detection. Based on series and several inline inspection versus MTNG inspection done, the estimated metal loss from the magnetic stress and the actual metal loss called out from inline inspection are within plus minus 10%. So this slide deck, this is the last slide of this presentation. It shows the blue line is the metal loss estimated from the MTNG, and this purple here is the metal loss from the orange, sorry, is from the inline inspection. You can see from here, they are not really accurate because they're not comparing apple to apple. However, the metal loss from the MTNG is estimated from using ASME beta-1G and proprietary algorithms. So they are comparable. So if you're looking at unpickable lines where inline inspection is not practical, this becomes a tool for unpickable pipeline operators. So if you have a buried facility line that you cannot deploy inline inspection to, this becomes a handy tool that can be used to estimate the metal loss on unpickable lines and help you prioritize areas of concern. But if the pipeline is pickable, you have inline inspection. It is good to supplement MTNG, especially in high critical situation or at bend situation where there's some stress level or you're doing some strength evaluation to be able to have two sets of data to predict areas of concern. So in conclusion, the result has shown the capabilities of this technology in the identification, characterization, and prioritization of defects that can help operators prioritize areas of concern, especially on unpickable lines. If it is pickable, it is also useful. You can supplement it with an inline inspection to ensure a holistic assessment of that line. Based on preliminary findings, the capability to estimate metal loss and other defects from above ground suggests that when this technology is being used with other tools in a unpickable line is going to be one of the effective ways of evaluating the condition of that line. And the last one, on high critical lines, this technology can also be combined with inline inspection to be able to show and address identify areas of concern, enhance evaluation of that critical assets, and ensure and minimize risk on that specific line. So thank you for listening to this presentation. My contact details is here. If there's any specific question we can't cover during the Q&A, feel free to send an email. This slide deck is going to be shared with ICorr, and you can access it on the website in case of any specific question. And there are backup information here. If somebody wants to read more about the technology, or you can see the backup slide. So I want to use the opportunity to thank the owners of this technology, IGSAT, for the opportunity, and also Canchux, for also ICorr for giving Canchux Corrosion Inc. Canada to be able to have this time to make this presentation. Thank you very much.
Right. Thank you, Dr. Chucks. We shall move to the Q&A session. If you could open the Q&A chat box and you'll see the open questions. There are 6 of them.
Oh, sorry. Let me see what I can see. They are okay. Within the step 2. Okay, let me take it one after that. There's one from Stephanie Okoye. Hi, Stephanie. During step 2, if the status of pipeline is evaluated to be in good condition based on CP level, coating and sorry, is there a need to proceed with? Stephanie, this is a very good question. So I'll answer this question this way. If we're conducting and like if it is a regulated line, like direct assessment is a regulated and a pipeline assessment technique. So approved assessment technique. So if we're conducting direct assessment, all the 4 stages from pre-assessment, indirect inspection, direct examination, and post-assessment shall be completed according to AMP SP 0502. So if you check the cathodic protection effectiveness and it's good, you check your coatings and the conditions are minor from DCVG, ACVG, ACCA, you check your soil is a very high resistive soil, that suggests that you may not have a problem, but SP 0502, which is a specification for external corrosion direct assessment, requires, you still have to expose the pipe to actual confirm that what was predicted is actual condition of the line, and then you cannot complete the post-assessment. This is where you're going to say, hey, I conducted the pre-assessment, there was no issue on this line, I worked on the line, the CP was effective, the coating conditions were the coating anomalies predicted were minimal, the soil was highly resistive, we conducted the direct examination, there was nothing found. If it is in the US for gas line, CFR Part 192, for gas line, that is going to be for 7 years. So the reassessment interval is going to be 7 years. But if it's for liquid line, Part 195 is going to be 5 years. So it depends on if there's any defect found during the step 3. But another point I wanted to add is, but if you're doing an engineering assessment, say for instance, this pipeline is piggable and you have run your inline inspection, and there's a specific area of concern, you can actually use DA as a supplementary engineering assessment tool. In that regard, say for instance, the inline inspection did not find anything, but out of curiosity, you want to check. You do your CP and everything, and CP is effective, coating condition is in good shape, and in that regard, you are not mandated to actually expose the line. But if the DA is the actual direct assessment technique you are doing, SP 0502 mandates you have to complete the 4 processes. The second question is from Divine Namdi. What makes MTAG2 unique compared to others in the market? I captured this during the presentation. The first one is there are other tools in the industry. But what makes the technology unique now is the fact that the technology is able to identify. Other technology can do that, but it takes it to the next level. It's able to characterize. So if I walk on buried line and I have a buckle or dent or have a metal loss or crack, this technology has gone to a level where it will tell the operator, hey guy, you have a metal loss, you have a crack, you have a dent, you have a buckle. And I want to add, this is subject to depth of cover. Provided the pipe is buried within 7 meters, you are able to identify, you're able to characterize. And the second point is, in terms of the prioritization, it takes that characterized defect and then prioritize it. So we're able to use the magnetic strength to estimate the metal loss using ASME B31G and proprietary algorithms, and then we're able to give operators the estimated metal loss. So in that instance, for facility lines, where inline inspection is not practical, you can use this technology to be able to prioritize areas of concern. If you're doing a DA, you can use this technology, your CP, your coating, your soil, then having information about the specific defect type and the priority is going to help the operator prioritize areas of concern, and that is going to improve pipeline safety and is going to minimize costs, that is where applicable. Next question from Stephen. He said, under what circumstance will you definitely not? Actually, I like this question. I like this question is a good one. So this technology has limitations. First, if the depth of cover is greater than 7 meters. I know I don't have audience from the US. Let me stick on meters. So if it is lower than 7 meters, it should be, your POD should be accurate. You'll be able to identify, characterize, and prioritize. But if it is greater than 7 meters, the POD might drop and the confidence may be questionable. And the second limitation, which may not necessarily be a limitation, is we want the length of the access line to be greater than 100 meters. There's some, yes, if you are interested, you can follow up with me through email. I can explain more just for the sake of time. And then number 3, we are able to do from 3-inch up. So if the line, 1, depth of cover must be less than 7 meters. 2, we recommend the line to be greater than 100 meters. If not, we're going to do a lot of back and forth, which may cause a little bit of logistics issue. And 3, we want the size of pipe to be smaller than 3-inch. Thanks, Steven. The next slide, you say, can NTNG be used when you have 2 or 3 lines? Oh, no, is that, okay, from Don, is that maximum pipeline diameter for NTNG? There's no maximum. The minimum we only do from 3-inch up. That one is straightforward. And the second one from Steven, can NTNG be used when you have 2 or 3 pipelines? We have a proprietary way. If you have pipelines on the same ditch, we are trying to differentiate one may be complicated. We have a proprietary way we can use to be able to figure that out. Yeah, that's a good question. If they are parallel to each other, the answer to your question is yes. Operationally speaking, yes, we have a operational specific way we can be able to address that. But that question is very good because if you're trying to locate a line, it may become very, very challenging to be able to figure out which line am I evaluating. But we'll have some ways in-house. Maybe Steve, you can send me an email or maybe we can have another chat just for the sake of time. I'll explain to you, but the answer to your question is yes. From Stephanie, what technique is best to identify condition of internal coatings and cladding? We have a new technology that also uses this similar technique. This one is passive in the sense that we work from buried line and then we use our captured magnetic field and determine defect externally on the line. If it is internal cladding, this technology is not designed for that. We are still doing a little bit of pilot program to be able to confirm the dictation capabilities internally in the line. When we are done with that, I will answer that. But for now, there's a different technology, Stephanie. So maybe if you can email me, I can recommend that technology. I'm not presenting that in today, but we'll have a tool that can support you in that regard. Somebody asked a question about the strength of my, let me check how my time is so that what is the strength of magnetic field? Yeah, so to answer that question, and can we assume that it's safe with not permanently magnetize any metallic object? Yes, it's a passive inspection in the sense that we are not inducing any, just like if you run MFL, you are inducing magnetism on the pipe. But if you want to do MTNG, to avoid any impact, like let me say, for instance, you run an inline inspection, we recommend we wait for 6 months before we can run the MTNG because it's a passive. You are not inducing anything on the line. You're just taking the sensor, working from above ground to be able to identify stress concentration because of magnetic field generated because of stress that is already inherent on that line. We have another tool, which if anybody's interested, email me. That one is actually active, where we can actually connect on the line. That one uses an active technique to be able to pinpoint areas of concern. But because of time, I will be able to skip that one for now. I have can interference such as crossing close to each other? Yes, that's a very good question. I think Stephen asked the same question. Yes, interference does not, let me clarify, interference does not affect MTNG inspection. However, we have an internal procedure to ensure that the specific line of concern is identified before we can conduct the inspection. Just like if you're doing CP surveys or DCVG coating survey, if you have anomalies in the same area, it might mask the accuracy of what they're doing. With MTNG, if we employ our proprietary methodologies to be able to pinpoint the areas of pipe we're evaluating, we are able to accurately determine the specific area of concern. I tested the method 20 years ago. It was very sensitive to the operator and depth of cover. How has, okay, from 20 years ago, yes, that's a good question. So the improvements are one, the depth of cover has increased of 7 meters. Previously, it can only detect buried pipeline within 3 meters. So now, if your pipe is buried to 7 meters, this technology can give you over 85% of probability of detection. So provided a pipe is buried within 7 meters, you can use this technology. Number two, previously, when you work on buried line, and if they are longitudinal, hoop stress, complex stresses act on that specific anomaly, previously, it was very difficult to figure out what's going on because there can be metal loss, there can be localized, there can be crack or a dent. We can just tell the operator, hey, something's going on here, but we didn't have that capability to be able to accurately, uniquely differentiate all those stresses. With this new technology, yes, we can tell the operator, at this specific anomaly, you have 3 stresses acting: hoop, longitudinal, and complexity on that specific anomaly. So that are the key improvements. There's another question. Let me see here. My comment with ICDA. Thank you, good presentation. My comment with the technique ICDA cannot be. For now, when it comes to ICDA, we are doing some validations because you know how the magnetic field is acting on the entire pipe wall. So we have some preliminary information to suggest, please mind my word, to suggest this technology can be used to detect internal defect. However, please watch my word, we need to do holistic and diligent validations to be able to confirm the internal detection threshold. For now, the focus is on external. When we have completed those diligent pilot programs, we'll be able to say with accuracy and confidence in terms of the threshold for internal. For now, the focus is on external. Will this method be useful to check CP effectiveness? In that regard, in ideal condition, if you have an effective levels of cathodic protection from, according to AMP SP0169 2013 standard, in ideal condition, if you have effective cathodic protection, you should not expect a metal loss, external metal. However, if you have a situation where the pipeline is buried and coated with a high shielding dielectric coating, in that regard, there can be a vacuum, a space created, electrolyte can go in, you can be conducting your CP survey, the CP protection might look appropriate where you're having external metal loss. So having a good levels of cathodic protection per negative 850 millivolts versus copper surface electrode instead of does not guarantee that you don't have external metal loss. It depends on levels of it. Do you have interference in the area, or specifically, what kind of coating is that? So, and that is why if you're doing a DA program and the pipeline is coated with a high shielding dielectric coating, this technology is very good because if you have a metal loss, it's going to capture that. Then number 3, generally speaking, if you have a good CP on the line that is effective historically, you should not expect any metal loss, and MTAG is not going to find any metal loss. So by not finding any metal loss is an indirect way of evaluating the CP is in good shape. Can we detect peak trap during ILI operation? Oh, okay, yes. This technology also has a unique application for inline inspection operators. You run your peak and it gets stuck. You can use this technology to accurately pinpoint where the stock peak is. Actually, this is one of the unique benefits of this technology. So you don't have to spend a lot of money digging the no. You just use the technology, scan it quickly. It tells you exactly where the peak is stocked. So you can use this technology. Also, we look at the cost. If we combine CPC with MTN, I think the cost will climb up compared to ILI alone. From my personal experience, inline inspection is super expensive. If you're doing a DA and combined with ATAG, I feel it's going to be more cost effective than inline inspection. I answered that. Do you have another question? Please, for questions, if there's any question I can't cover due to time, feel free to send me an email. We are passionate about this technology. We are passionate to collaborate with the operators to ensure the goal is to make sure the pipeline is safe, and we are employing the best practices to ensure safety of buried pipelines. The tool looks okay. The tool does not guarantee any magnetic. It is only yes. If you are doing a coating survey, just to expatiate, if you are doing a coating survey with DCVG, ACVG, you are receiving the magnetic group, sorry, the voltage gradient, which is a result of coating because of the current density at the coating anomaly location. So the voltage gradient is what you are actually capturing. This is for coating survey. In MTAG situation, you are capturing the magnetic field that is already being created due to stress. Dr. Islam, that's a very good question. Say yes, we are receiving the magnetic field that is already generated due to stress that is impacting or inherent on that buried line. Please, I don't know whether there's another. I think I think I've addressed. Let me see whether there's any question. But anyway, generally, if there's any other question that I did not address, please send me an email. Let me make sure I share my email. Send me an email. My email is here. I'll be able to address your question. But generally speaking, there was extensive R&D done to be able to improve this technology where it can confidently identify, it can characterize, it can tell you exactly the kind of defect, and it can prioritize. And we have done extensive validations on pickable lines with inline inspection and actually exposing the line to give us the confidence that in unpickable line situation, we are able to estimate the external metal loss, and it is within plus minus 10% of what inline inspection would have called. So we have validation data, and in addition, we have a third-party company that has conducted quality assurance on this technology and the methodologies and certified it okay and acceptable for pipeline inspection. So I think this is the end, me, and thank you for giving me the opportunity.
Yeah, thank you, Dr. Chucks. That was very impressive how you got through the questions. Yeah, so if you've got any more questions, just email Dr. Chucks directly. And yeah, we'd like to thank you.
Hold on. Sorry, somebody asked, what is the difference between DCVG and MTAG since they are both no. Let me answer this one, me. And the last to respond to this, so DCVG is like if you're doing okay, it's not really it's not, I wouldn't say it is non-contact if you're doing DC because you have your voltage gradients, you have your, let me quickly run and explain this question. Somebody asked me a question, the last one. If you're doing DCVG, you are working on from very above ground and you have your voltage gradient. So you're actually contacting the soil. It's not contact in the sense that if you're doing CP, you are connecting your copper wire to the buried line. DCVG in that regard can be called non-contact because the two probes are not touching, like, see, this is the DCVG. The probes are touching the soil, but it's not touching the buried line. If you're doing CIS, it is contact in the sense that the copper wire is connected to the buried line through the test connection points. The key difference between MTAG and the DCVG is that DCVG focuses on giving you the voltage gradient that is indicative of the coating fault on the line. MTAG captures the magnetic field and magnetic stress that can be used to characterize and understand the defect type. DCVG have a coating fault, but it doesn't tell you whether you're having a metal loss in that coating fault. You can use the effectiveness of cathodic protection to be able to predict. However, MTAG is going to tell you you have a metal loss and the depth if required. Number 4, MTAG is based on measuring the magnetic stress. DCVG based on measuring the voltage gradient. Both techniques can be supplemented to improve the strength and weakness of each other when combined in a holistic DA approach. Thank you.
All right.
Okay.
Thank you very much. Right. Thank you so much. And yeah.
Okay. Thank you. I will stop sharing my deck.
Right. Okay. Thank you. And I shall end this webinar right now.
Okay. Thank you. Thank you, everyone. Thanks for coming.
Right. Bye.